Welcome to Chapter 9 Hypothesis Testing. This is the beginning of the hypothesis testing sequence. Having gotten through Chapter 8, where we're looking at some confidence intervals and how they play out, and looking at interval widths and where a certain percentage of observations or means would fall within a particular boundary, hypothesis testing is going to take us in a similar direction, except that we're going to draw samples now and see what we can do to knock down a straw man. Now, what I mean by that is we're going to set up a null hypothesis, which is a status quo, and see if we can disprove it. It sounds kind of funny that our goal is to knock down what is often held to be true, but why else would we do a hypothesis test? So what we're going to try to do with this chapter is look at defining the null hypothesis and the alternative hypothesis, the null being the status quo, what is commonly held to be true, the alternative, which is what we're trying to focus on. Then we'll talk about two types of errors, type 1 and type 2. We'll be able to focus a lot on type 1 because we can control that. Type 2, we can't control as much, so we don't talk so much and work too much with it, but we will have a little bit of introduction to it. Then we'll talk about the hypothesis tests themselves using the p-value approach. Now there is another approach called the critical value approach, and you often see it in your textbooks. We're not going to use that one. This is an Excel-based course, and this is business statistics, so the p-value approach lends itself very nicely to Excel and the functions in Excel. The last thing we're going to do is just kind of figure out what happens when we do this. What happens when we draw the statistics, and what does it mean for us moving forward when the sample is being compared to the mean and we actually reject or do not reject a null hypothesis. So here's an interesting beginning. So we want to know, are college kids studying hard or hardly studying at all compared to what happened in the past? So there's a recent study out that says that, well, out 6-7 years ago, asserts that over the last 5 decades, the number of hours that college students, on average, they study each week has been dropping steadily. Now, we're looking at a study in 1961 that where students on average spent 24 hours a week. Today, students in a recent study now only studying 14 hours per week. Now, we don't know if it's been some kind of steady drop. We just know that it was 24 and 14. So bullet 2 really isn't the best way to say it, but we do know there has been a drop. The question is, we have a large university in California, and they want to know if the trend reflects what's happening at this university. So what they're going to do is go out and take 35 students and ask them about the amount of time they spend per week studying. And then when you use this result, you want to test to determine if the mean study time of students at this particular university is below what we saw in 1961, which is 24 hours. So it's a less than. Is the time below that number? Also, we want to see if the study time for the current students at this university is different than the 24. So it's two different tasks. So the first one would be if it's less than 24, and the second would be is it different than 14? Now, hypothesis testing helps us look at competing opinions. In this case, we'll call them hypotheses. As I said before, the H sub 0 is called the null hypothesis. This is what we presume to be true, or the status quo. The alternative hypothesis, H sub A and sometimes H sub 1, is the contradiction to it. Now, it's a number line sequence completion. In the null hypothesis, there will always be an equal sign, less than or equal to, greater than or equal to, or just equal to. The alternative will be less, greater, or not equal to. And in doing this, we're going to be able to talk a lot about the null hypothesis, but our rates will talk, and the data we pull and use will be valued against the alternative hypothesis. So as we saw before, leading into statistics, we're going to use sample information and use it when we don't know a lot about the population parameters of interest. So we'll draw the sample, create the statistic, and make best use of them against the population's parameters. That's just the general idea of statistics. That's why we call it inferential statistics. Can you tell a story about the population? We want to know if in drawing the sample, we gather enough evidence to reject what's happening in the status quo or the null. Now, if we can, we reject. If we can't, we do not reject the null. We'll get to that here in a bit. So if we gather enough information, we'll reject the null. Our sample evidence is inconsistent with the null and is overwhelmingly in favor of the alternative hypothesis. However, we will never talk about the alternative hypothesis in our final statement. We either reject the null or do not reject the null. We never accept the null hypothesis because we'd have to have absolute evidence that this is the case. We don't need absolute evidence. All we need is a little bit of reasonable doubt to make sure that this thing is allowing us to not reject or reject in this case. So we don't have enough evidence to say accept the null. We have enough evidence to say we do not reject. And we'll talk about why that is here in a bit, because it is a case where absolute knowledge is necessary if we want to say accept. Now, the null hypothesis, the alternative hypothesis, H sub 0, H sub A, what we're trying to do when we define them is simply look to those things that I pointed out before. With the null, we will say, if you can follow along, equal to, greater than or equal to, or less than or equal to. And they're compared against equal to not equal, greater than or equal to less than or equal to greater than. The contradiction completes the number line. So this would be all values from greater than or equal to a particular value, and then less. So it's all numbers in the complete number line from negative infinity to positive infinity. Same here, same here. You're either exactly equal to it or you're above or below. I don't care which one, you're just above or below. Make sure you get that right when you're looking at your hypotheses. The equal always goes with the null. And as you saw, there's two types of tests, obviously. There's the less than or equal to or greater than or equal to type, and then there's the equal to type. Now, the equal to type is the type 2 style. We call that the two-tailed test. Pretty common way to look at something. You can reject the null when either side, you're not directionally obligated to reject. So you could reject in the lower or upper tail. And by lower upper, just follow the beak. The beak in the alternative hypothesis points to the left, it's lower tail. Beak to the right, it's upper tail. And this would be a two-tailed test. So the two-tailed test is always equal in the null and not equal to in this one. The not equal to tells us that that distribution can be made for rejection in either tail. Remember that. Please remember that. The one-tailed test, right tail, notice the beak points to the right. Left tail, the beak, or in this case, the less than sign points to the left. That's exactly what we want to be able to accomplish when we start laying this out. And when we do this, we want to simply lay out a system for hypothesis testing. What are we trying to accomplish here? What statistic is going to be used against a parameter? Is it going to be x bar versus mu? If you did proportion, is it p bar versus p? And so on. You can even do them versus some kind of a variance if you'd like, or a standard deviation. So once you know what you're going to test, you decide, is it a one-tail or two-tail test, lower, upper, or both? From there, you would figure out the type and lay out your hypotheses, create your statistics, and create a value that allows you to determine a rejection or do not reject. For example, pretty simple. To get started, you have a particular trade group that predicts that back-to-school spending will average $606.40 per family this year. Will average, that's an exact value. A different model is needed if the prediction is wrong. So it's will equal this or won't equal that. Very simple two-tailed test. We're trying to predict the mean since we're saying average. So we're going to test the average, the mu, and it's going to be a two-tailed test as described. Mu is either equal to that or it's not equal to that. And from this, we will look at errors. We're able to create this layout knowing that sometimes I'm going to reject the null when I shouldn't, and I'm not going to reject the null when I should have. Those are two types of errors. There's type 1, we reject the null when it's actually true and we shouldn't have. pretty common, and this is what we assign a probability, and that probability is alpha. And the reality is, when you do a hypothesis test, you have to lay everything out in advance. Here's what I'm testing, and here's the alpha level that we're doing. That's the type 1 error probability. Type 2 is when you do not reject the null when you really should have. Those are called power tests, or beta. And the power of a test is 1 minus beta. It's a complicated form using curvatures. So we'll have these power curves. Higher level statistics, we're going to focus here on type 1 errors. And it will all be done with the idea that I, as the experimenter, are going to lay out what alpha is. Alpha is going to allow me to see where the rejection falls. I'm going to create a probability. If that probability is less than that particular value of alpha, then I will reject the null. If it is not less than or equal to, I won't reject. So the type 1 error is rejecting the null when the null is actually true. So you've made a mistake. So we'll talk about that. It's kind of a sliding scale as well. You're able to, if you increase alpha, you decrease beta. If you increase beta, you decrease alpha. So what we're going to do is work our way through this. So let's look at this. The basic layout for these mistakes are: I reject the null. Null is true. That's a type 1 error. I don't reject the null when I should have. That's a type 2 error. The others are correct decisions. Pretty simple, but let's think about it from a grander picture, so one that makes a little more sense. Court of law. When someone goes into the court of law, if they plead not guilty. They really don't plead innocent, because you'd have to have absolute proof to prove someone is innocent. So you're either not guilty, that's assumed to be true. You walk in innocence or not guilty until proven guilty, or you're guilty. A type 1 error would say you put a guilty, you find someone guilty when you shouldn't have. So essentially, you're putting an innocent person in jail. A type 2 error would say that you're letting a guilty person go free. There's a lot of other ways to look at this, but just remember, type 1 error is putting an innocent person in jail. If we set the alpha level, say at 5%, you're allowing up to a 5% chance of putting an innocent person in jail. You have to determine which will it be. Will it be 5? It'll be 1? It'll be 10? Most of the time will be given in statistics classes, but the reality is, in the real world, when we present this as a case, we will have to set this up ourselves, and it has to be done a priori. So what are we going to do? Well, there's two kinds of tests we'll discover here. One is when we know sigma, so that's a population known type. And then there's one when we don't know sigma, so we'll have to draw a sample and use the sample variance, or sample standard deviation, S. In this case, we're going to have and set up our null. We're going to set up the alternative hypothesis, and we're going to create this statistic p-value and see if it's less than or equal to alpha. If it is, then we will. If it's less than or equal to, we'll reject. If it's greater than, we won't reject. We're not going to do the critical value approach if anybody's concerned, but what we want to do is make sure that we're using Excel as much as possible, because it gives us really precise values for the p-value. So how do we do it? Well, you're going to be given information. When you use the information, you'll be able to create a statistic, and that statistic, when we know sigma, is z. So in this case, what we'll do is we'll say, here is a value z. We'll draw a sample. Its mean will be x bar. Here's the value that we're trying to knock down from the null hypothesis, and we'll use the standard error, the sampling distribution of the standard deviation of the sample mean, and we'll use that to create a statistic. You've seen these statistics before. This isn't new. What we'll do is create a probability and come up with the idea of a p-value where, now get this, it's the probability of seeing what you just saw with the null being true. So if the probability of seeing what you just saw is really small, I mean, think about this. You go out and you draw all this information in and you create a statistic, and the chance of drawing that statistic is, say, 0.0001%, yet you saw it. you saw something that's almost impossible to see. So therefore, what was once thought to be true is probably not. You've just gained evidence to say what was once thought to be true, you, is probably wrong. And we're going to change it by saying we're rejecting the null and something has changed. If the probability of seeing what you just saw is true, given that the null is true, you reject. That's what the p-value tells us. It tells us, are you as extreme or more extreme than what's drawn from the sample? And we'll set the assumptions up with p-value. So again, anytime you see inequality, it's in your alternative hypothesis. We're looking right tail, left tail, two tail. The two tail is nothing more doubling up the probability because you're having to look in both directions. We'll look at some problems. If that p-value is less than or equal to alpha, we reject the null. Now, just a sidebar here. Remember, anytime you have a continuous distribution, it doesn't matter. It could be z greater than z, it could be z greater than or equal to z. It doesn't matter because you cannot have at value probabilities. The probability of seeing a particular instance in a continuous distribution like normal is 0. It doesn't happen. Moving on. The left tail test, if you can find your statistic out in the outer tail, you reject. Upper tail, you reject, or two tail. It doesn't matter which one. As long as it's there and it's less than or equal to alpha, you reject. So what we'll do is we'll set up the hypotheses. We'll set up the test statistic, get its value, convert it to a probability based on p-value, probability of seeing what you just saw given the null is true. If it's really small, we'll reject, state the conclusion, and try to see if we can do some different kind of interpretation. So here's an example. Let's just set this up. You know of a sample size 25 that the sample mean is 71 and the population standard deviation sigma is 9. We know that forever and always the mean wasn't 71, it was 67. What you're trying to do is prove that it's more than 67. Now, right off the bat, 71 is greater than 67, so you know it's going to be in the upper tail. The question is it far enough into the upper tail to allow us to reject the null and say that it actually is greater than 67? So we know all this information. 71, sample mean, minus 67. Here is your standard deviation. Here's your sample size. Square root, so that's 5. And you get a z statistic of 2.22. Now, we know a couple of things already about how these things work when looking at the empirical rule. We know that within one deviation either way, about 67%, 68% of all observations fall. With two deviations, about 95%. And within three deviations, just about everybody falls. So this is a little over 2, so that means there's 2.5% in either tail. So you're way out into the upper tail. But most likely this would be a rejection. So to create this thing in Excel, let me just toggle over here real quick and show you. Here's what I would have done in Excel using the z statistic. Here's sample size. Blow this up a little bit. Sample size. Here's what was ever and always believed to be true, standard deviation. Here's the sample mean. I calculated the standard error here. This up for you a little bit. See it? Standard error here to be 9 divided by the square root of 25. And so my z statistic, as it was laid out before, is nothing more than x bar minus mu divided by the standard error. Great. Pretty simple to do in Excel, and I'm going to have this available to you in your course module. Now the question is, now that I have some idea of a hypothesis, we have a statistic, I need to take this and figure out what its p-value is. Well, we know that 2.22 is way out into the upper tail. Well, I need to figure out what way out means. So I want to know what's the probability of being greater than or equal to 222 or greater than 2.22. So So what I'll do is, since it's a upper tail, right tail test, I want to look up towards positive infinity. So I'm going to be looking to the right. So what I'll do is start by looking at how in the world does the p-value get created in Excel? Well, the p-value is a look back for the z distribution when sigma is known. So looking from left to right on the normal curve, I would think that I'm in the upper tail, looking down towards negative infinity. So I will use something called norm.s.dist. That's the normal distribution that's been standardized. And anytime you see the letters DIST, it implies that you're using a probability. I want to know what the z value is, and the true means looking back all the way up cumulatively. And what this does is it gives me the probability of being less than 2.22. Well, you're looking down on the lower 98.68% of all observations. So the complement 1 minus would be what you're looking up to. So the p-value would say that looking up, you're in the upper 1.3%. Now, that's pretty far out into the tail. So that's what's happening here. We're looking down on, from this spot right here, looking left down onto the lower 98.68%, and we look up towards the upper 1.32%. Pretty nice. If we set alpha to be something, now we would do this beforehand, but let's just say we set it to 5%. 1.32% is less than 5%. Therefore, we would reject the null and conclude that the null hypothesis is not true, and we have an opportunity to change something given our data. If our alpha was 1%, 1.32 is not less, we wouldn't reject the null, and we'd say everything is fine. But if we had a value larger than 1.32 as our alpha, we would just reject the null. We have evidence to say that something has changed. Here's just a simple way to do it. Another way to do it, again, I'll have my values out. This is commonly held in your books. Another thing to look at is a two-tailed test. It can also be seen as a confidence interval. Now remember, a confidence interval tells us between these two poles what percent of all observations fall. Well, the interesting thing about a hypothesis test is if you can create a hypothesis test with two sides that creates a confidence interval, if the value of your test statistic from your sample falls within the confidence interval, then you do not reject the null. If it's outside, you actually do reject the null. Pretty simple. But you can also run it as any other kind of test. And we'll be doing all kinds of problems like this. So if it's in the interval, you don't reject. If it's outside the interval, you do. And it looks just like this. Now the interesting thing is that you already have X bar, you have sigma, you have N, you would be playing with alpha. You would just have to use a Z value. Let's take a quick look at this one. What if I use this idea and set alpha to 5%? Well, since I'd have 5% total, I'd have a lower 2.5% and an upper 2.5%. This number should look really familiar to you, 1.96. What that is, it's where the poles are for lower and upper, negative 1.96 and positive 1.6. Almost 2. Remember, 2% when we look at the empirical rule, within 2 deviations, about 95% of all observations fall. Well, see, now we have this value. Then 2, either way, 95% off of fall. Here's your 2. You would just then plug this in for Z. So back. What happens when we don't know sigma? Well, it's just simple movement from Z to T. Now, I don't have to go back and tell you about the T distribution. You've already seen that before. But what comes into play now is the T distribution, which is based off of this idea of degrees of freedom. In this case, it's n minus 1. That degrees of freedom will be used in calculating your statistic when it converts to a probability. Now, this should look a lot like Z. X bar mu n. Now, instead of known sigma given to you, now here's your sample. Here's reality, folks. It's very rare in the real world that you know sigma. More often than not, don't know you have S. So the T is more common than Z in the real world. But if your sample size is big enough, if you can get your sample size up, as you've seen before with the large numbers, if you can get that number up to, say, 100, if N is 100, T becomes Z, which is why we tend to focus a lot more on T statistics. We want large samples, that T becomes Z. How about this? Sample size of 35. We think that 14 is ever and always equal, or it's not. So it's a two-tailed test. What we're going to do, draw the sample 35. We have 1637 as the sample mean. We do know that the sample standard deviation drawn from this mean of 16.7 is 7.2. That's a pretty darn big deviation for this sample. Notice 16.37 is greater than 14. That means it's going to be upper or right tail of a two-tailed test. So you're still going to have to look back and figure this whole thing out. Calculate the T statistic. In this case, 1637 minus 14, 722. Just pulling the square root of 30. It'd be better if this was a perfect square of 36, right? And you get about 1.94, pretty close to what we saw before. Now we have to do a conversion from that value, T, to a two-tailed p-value, degrees of freedom, not 35, but 34. Let's take a look. So here's what we have. Here's the T statistic. Blow this up a little bit for you. It's 35 is your sample size. Forever and always has been 14. 7.22, 16.37 is your sample mean. Again, the standard error is nothing more than S divided by the square root of 35. Therefore, the degrees of freedom are 1 minus the sample size. And our T statistic, nothing more than 37 minus 14 divided by 1.22. I told you the T value is going to be positive because I knew 16.37 was greater than 14. Here's the kick. While the normal distribution with X was looking back, the T looks up, looks to the right. So remember, it was to get the upper tail in the Z distribution, I had to do 1 minus what the lower was, because we could only calculate using lower. Here, though, we're going to calculate looking into the upper and do 1 minus it to get lower. You'll see what we do. So I'm going to take my statistic minus my degrees of freedom. I get a p-value, 3%. But that's an upper tail, single tail test. I know that I have to double that because my alpha has been halved. So I can keep it at 3 if I compare this to half of an alpha. If I want to compare it to a whole alpha, I have to simply double it. I can just multiply by 2, or Excel gives me this neat little trick where I can do T distribution, dot dist means probability, and 2T means two tail, T is freedom. Pretty slick. There is a way to do it with tables. Those of you had stats like I had it years ago, 20 years ago, we would use this table to look things up, but Excel has given us the precision that's necessary. Any package, SAS, SPSS, whatever, has this level of precision now, and it's very helpful to be so precise. We know now that it was about 3%, and in that case, we have this value, and if we set alpha, let me go back to it, if alpha was, say, 5%, we wouldn't reject because this is bigger than alpha. If alpha, say, was 10%, this is less than alpha, we would reject. Straightforward. So if we don't reject because we said alpha was 5% and we knew the p-value was 6, we don't reject the null, and we conclude that the study time of students at that university, remember this was all about that university, so the study time from that university, which was 16.7 already lost it in my head, 16.37, that 16.37 is not statistically significantly different than 14. Therefore, we don't reject the null and we conclude that, hey, that university is no different than the national average of today. Hopefully this makes sense. Here's another way to do it. So just think about how you're going to set these things up. What does your hypothesis say? Okay, here's my hypothesis. We're testing means, proportions, deviations, whatever. Is it a z or a t or whatever, chi-square at some point? And what test statistic will I use, z, t, whatever, and then converting it to p-value appropriately, conducting a test based off of the a priori set up before alpha, which you control, which is the probability of a type 1 error. Do the test and give me a conclusion. If you can get through this, all hypothesis testing will make sense. Single, to ANOVA, and then ultimately to regression, which is where we want to go. Hope this helps. I'm going to put some videos out soon about how to do some specific examples in Excel for you to see to help with all your problems.